then say that this state is the same in the end. So essentially, if you combine these things inside the box, okay, this whole thing is now inside the box, okay, you can just say this thing to be something we call a phase query black box. The phase query black box is equivalent to giving, if you have x, the phase query black box can work and give you -1 to the power fx x. Okay, so you see this is of course e to the power I pi fx phase. Okay, so you can encode a function in the phase from a place where a function is encoded in the output, like an usual computer, just by putting a second qubit in this 0 - 1 position. Okay, if you had functions with this works, of course, also when this x is so I have also assumed x to be here to be just 0, 1, but works for arbitrary dimensional x and arbitrary dimensional function. Okay, so you just have to choose the dimensions of these systems appropriately. Okay.
But sir, you are not getting x. You are getting 1/√2 0 - 1.
Yeah. So this is the same state. 0 - 1 state remains 0 - 1 state. Okay. The whole unitary transformation, what it has done is, so what I'm hiding here is that there's a 0 - 1 here. Okay, I can denote that as minus, and also here, but it's kind of part of the machine. I've included it inside the machine, so it remains the same, and the phase I'm ascribing it to here. Yeah, the phase is applied to the whole state. Okay, but one of them is part of the machine. Okay, so this is how you can get something into a phase. Okay. Now the simplest application in an algorithm of this is this this thing, which is the
from the phase. If fx is 0, then I can see that the phase is going to be 1, and if x is 1, phase is -1. But if it takes many values, then
yeah, you can still. So what you have to use in these cases, okay, is you have to use superpositions with roots of unity, okay, and then that will also multiply there, so it will not be pi. Yeah, and you can do various things. Okay, so now the where was I? Okay, so the simple algorithm, the first historically was Deutsch algorithm. You see, quantum computation was first proposed by Feynman in 1981 or 82, I forgot, but in the context of simulating large quantum systems. Okay, and the reason was very, very obvious. Okay, the quantum systems have 2 to the power small n size matrices, and you cannot apply it in classical machines. But if you have small n qubits, it's just that much in space, small n occupancy. Okay, and there was some interest then how to do it, how to do universally, but there was no computer science kind of slant to it or angle. So that's what I think David Deutsch first gave. So it is a artificial problem. Okay, and there you have this 2 to 1 speed up. Okay, so all you do is you have given, okay, is the following, a function. Okay, so if you given x, okay, x is in this domain 0, 1. Okay, so not domain, so x is either 0 or 1, so it's the set. Okay, and fx is also in the set 0, 1, but there's a promise. That's the thing. So these are algorithms a bit artificial because they have a promise. Okay, the promise is that fx is balanced or even. Okay, balanced essentially means like odd. Okay, so fx is either now you see, so this will be more important in the next. So sorry for my. So we don't need this for this algorithm. It's for its. This is here. This condition here is obvious. This either that. Okay, either f of 0 is, so either both the f's for 0 and 1 are the same or different. Okay, so when you it comes in a different algorithm what I was writing, okay, at the next generalization. So given this, okay, so what is to be find is whether fx is whether fx is balanced or even. Okay, balanced means it's f0, f of 0 is 0 and f of 1 is 1, then it's balanced, or vice versa. Even means they're both for 0 is f0 equal to f1 essentially. Okay, so you want to find whether the function is like that or like that. Okay, yeah. Now this is really a toy illustration. Okay, now classically what will happen? Okay, this is the interesting thing. Okay, classically you see, so you how many evaluations of the function will be required. Okay, so of course you have to give x equal to 1, x equal to 0, get get f of x, then you again have to put x equal to 1 and get no, not implies, get f of x. Okay, so essentially you have to evaluate f of 0 and f of 1 to know whether they are same or different. Okay, so at least two, so two evaluations. So it's completely trivial that you at least will require two evaluations. Without that you cannot tell whether the function is balanced or even. Okay, but quantum mechanically it is very simple. Okay, all you do is you first prepare what I was calling the starting state of all quantum computation, only that now there is a single qubit, so it will just be 0 plus 1. Okay, now you give the black box evaluating fx. Okay, so you will get 1 by root 2, okay, minus 1 to the power f0 0 plus minus 1 to the power f1 1. Okay, so you see if they are not matching, so when the function is balanced is the word they used for odd kind of function, but like different, but it's not really odd, means it's not minus 1 plus 1, it's 0 and 1. So when they are different, in other words, then you will get plus minus of the so let me write the plus minus a bit outside, of 1 by root 2 of 0 minus 1. Okay, because these two phases are not the same, so you will go the minus state. You will have a factor plus minus outside you don't care about. Okay, and when it is even, that means you stay with the state 1 by root 2 0 plus 1. Okay, so you see these are orthogonal states. X basis eigenspace is fully distinguishable. Okay, so immediately you know, you measure. Okay, you might do another Hadamard. So this is the, so you see this is the thing which is happening in the, this is now a 2-slit interferometer. That's the phase application. And then before doing that, what they do is they do another transform here, which in this case will be another Hadamard, to bring it to 0 or 1. Okay, 0 minus 1 goes to 1, 0 plus 1 goes to 1. But you do not need to do that. You already know these are orthogonal, so immediately. Yeah. But how many goes of the black box did I require? Just one. Okay, so you have a 2:1 speed up. Okay, so not very impressive. Okay, now then Deutsch and Josa. So this is probably sometime in 1986 or 85, I don't remember exactly. But in 1992, Deutsch and Josa gave a version where you do get an exponential speed up, but only from the worst case. Okay. But in case of brevity for time, I will avoid that. I'll jump to the next toy algorithm, which is the Bernstein-Vazirani algorithm. Okay. So this gives a speed up which is always there. Deutsch-Jozsa has a speed up, but only in the worst case. Okay. So we don't want so I'm just skipping that for time. It's of some interest, but it has a very strong promise. There you make the promise of even or odd. Okay.
Can I ask, historically, were these papers published in physics journals or computer science journals?
This was published in Royal Society, Proceedings of Royal Society, or philosophical. So obviously these fields were quite kind of, out of the mainstream that time. So I think Deutsch just published in this either Philosophical Transactions or Proceedings of the Royal Society. Okay. Now the Bernstein and the computer, the one I'm telling now must have been a computer science and probably a conference proceeding. Okay, Bernstein-Vazirani. Okay, so I mean Umesh Vazirani is a computer scientist in Berkeley. Bernstein, I don't know what his background is. Okay. Now this was probably something like 1993 or 1994. I'm not like around that time. Okay, after the Deutsch-Jozsa. Okay, this will give you, rather than 2:1, will give you a small n:1 speed up. Okay, which is always there demonstrably. Okay, but the algorithm also has these kind of promises. Okay, so there's given. Okay, so there's something given, which is that there's a x, okay, which actually goes from this whole domain of 0 to 1, which means it goes from the function x goes all the 2 to the power small n values, all zeros to all 1. Okay, that's the domain of the function. Okay. Now, what are the values the function can have? So the function, we are given a black box that can evaluate fx equal to a dot x. Okay. So what is a dot x? A dot x is defined the following way. It is a1 x1 modular sum a2 x2 modular sum xn. Okay, where a is a bit string, a1 a2 dot 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 an, and x are all possible. So x1 is the first bit, x2 is the second bit. Okay, so x has values from all zeros to all ones. Okay, so x is x1 x2 dot 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 xn. Okay, so these are binary strings. Okay, so all zeros to all ones x goes, and then you have an unknown hidden bit string a1 a2 an, which you don't know the value, 0 1 1 0 1 1, whatever it is. There is a black box which evaluates this function a dot x. Okay, and where the dot product is defined by this modulo 2 summation. Okay, so its value is 0 or 1. Okay, so you do a1 x1 product, which is either 0 or 1. Okay, and then you add modulo 2 additions, you always get 0 or 1. Okay, so that is the a dot x. Okay, so now this is given. Okay, now find, what do you have to find? Find is a. That's what you're tasked to find. Okay, now classically what will you require? Classically what would you require? Okay, classically what would you do? You would first give the input x equal to 1 0 0. First you put that x. Okay, and you will get, what will you get with that? A1. Okay, then you give x equal to 0 1 0 dot 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 you get A2. Okay. So obviously you require n evaluations of the black box. Okay. So classically it's kind of a no-brainer to see that you cannot do with less than that. You have to have small n of those things. Okay. Quantum mechanically, you will see a wonderful magic. Okay. Quantum mechanically, what will happen? Quantum mechanically, you will we will do this Hadamard. So we will start initially with this equal superposition. We always start in quantum computation from x equal to 0. We go up to n minus 1 x. This is the one easily created by Hadamard. So in some quantum computation books, or when people draw circuits, you will see also that people start from 0 and write the Hadamard. So I don't write that step, because this is a thing you easily do and you always do. Okay, almost always do. Okay, in the new variational algorithms you don't necessarily do this. Okay, but then what you do is you do the black box evaluation of A dot x. Okay, just once now. So what will happen? This will go to 1 by root n, okay, x equal to 0 to capital N minus 1, okay, minus 1 to the power a dot x. Okay. So you see this evaluates this function. We know how to put this function in a phase. Okay. So anything which evaluates the function, we can with extra 0 minus 1 put it in the phase there like that. Okay, and then x, right? Okay, so this is where we have encoded the problem. The A dot x is now been evaluated, but evaluated in the superposition of all the components. Okay, so now what you do is this Hadamard transform, h to the power n. Okay, so now what I will put you as home task, it's very easy to do. Okay, so if you do Hadamard on each qubit, so okay, so let me just write this thing. Hadamard can be compactly written, say for the jth qubit. Okay, it can be written as sum over yj, okay, where yj is just element 0 or 1. Okay, 1 by root 2, okay, and then minus 1 xj yj yj. Okay, so it summarizes both the results. So Hadamard to 0 goes to 0 plus 1, Hadamard to 1 goes to 0 minus 1. So this is just writing that, okay, compactly. Okay, but this helps you to write also this thing, Hadamard transform, which is doing Hadamard on everything on x. So you do nothing but do this n times. So h acting on x1, h acting on x2. Okay, so okay, so maybe I will write h acting on x1 cross h acting on x2 like that, h acting on xn. Okay, that thing that can be that is compactly written as 1 by square root of 2 to the power n times sum over y. Y will again go from 0 to this 2 to the power n minus 1, but minus 1 to the power x dot y y. Okay, where dot product is defined in exactly the same way. Okay, so it's very easy. Just take n of those things and you'll get that. Okay. Okay. Now you will have to use one thing, that when you have powers of minus 1, then normal addition, yeah, becomes same as modular addition, right? Because you have even powers or odd powers, so it becomes, yeah. So then you can do that. Okay. So yeah. A's are also is a bit string. Yeah. So each of those A's are this is a bit string. So each of those are 0 or 1. Okay. So so now when you do this Hadamard transform, if you accept this for this formula here, okay, which I suggest that you just check out at home, okay, just multiplying many of these compact ways of writing the Hadamard, okay, then you see what happens is this goes to 1 by root n x equal to 0 to capital N minus 1, okay, minus 1 to the power a dot x, okay, and then this is not just x, but now I am summing over y as well, okay. So I am doing this Hadamard transform. You see there is one more 1 by square root of capital N, so this will become n. There was one root n from there, another will come from the new transformation. This times minus 1 x dot y y. Okay. Now I am telling that this is actually equal to a. Okay. So all you do is just measure that final register. Okay. Why? Let me I mean, people can justify me, but let me justify you just in a very simple way. So choose the case that y is equal to a. Okay. Then that is x dot a. So this is minus 1 square. So it's plus 1. Okay. So for y equal to a, you sum up, okay, n terms, okay, which are x, okay, which are all plus 1. So n by n is 1. So the amplitude of a is 1. Okay. However, you see all these are unitary transformations. I have only done unitary transformations, and I have started with a normalized state, right. So if the amplitude of a is 1, means the amplitude of everything else is 0, right. So that is a after the transform. So all you do is just measure and you find the bit string a. And how many times have I used the black box? Just once. Okay. So quantum mechanics here gives you a small n to 1 speed up. Okay. Yeah. A is not continuous, but a can be very large bit string. Yeah. So yeah. So it's this, so you can say a can be discretized in some way if you are thinking it a limit of a continuous function, but typically a is a bit string. So a is you know, some unknown bit string essentially 0 1 1 1 0 1 whatever, yeah, and that to find, you will at least classically you will at least need to evaluate it, feed in. If this thing is only giving you a dot x, you have to, you know, do a number of times. But quantum mechanically, because of this you know, superposition and then the Hadamard transform, you can just get a in one go. Okay. So this algorithm I very much like, because it's kind of a very classic demonstration of quantum speed up. It's concrete, and there's no kind of probabilities, and in case of this deterministically there is this speed up. Okay. Of course, this kind of speed up is not very useful, because you see there are 2 to the power small n steps, and this is just you know, a polynomial speed up. Okay. So there was soon an algorithm by you know, by Simon's algorithm, which gives the first you know, shows the first exponential speed up. Okay. So that is also quite a contrived algorithm. So I'm thinking maybe since we will do something similar for Shor's algorithm anyway, we perhaps skip that, okay, and directly proceed to that. So how are we doing for time now? It's,
you have 10 minutes.
10 minutes, okay.
According to the 1 hour thing. But
Right.
5 minutes later.
Right. So I think just because I have 1 more hour left on Friday, maybe Simon's algorithm we will skip at this stage. It's kind of instructive to do that for Shor's algorithm, but since we'll do the Shor's algorithm anyway, we do not do the Simon's algorithm. Okay.
Simon was also a computer scientist.
Yeah, yeah, yeah. I don't know exactly. Yeah, but it was yeah, somewhere in one of those universities, Berkeley.
Does this come up with any good algorithms?
I would say only Eddie Farhi, this quantum adiabatic algorithm, which is very generic, right? Yes. So and Grover, which I will speak about. To be honest, Grover was not really a computer. Grover was an electrical engineer. So, electrical engineer is like almost physicist rather than so. I don't know. Yeah, yeah. But anyway, I think what happened is they had a lot of physics colleagues. They were very embedded in a physics environment. Okay, because I think Grover was in Bell, AT&T Bell Labs that time. So probably was in a very okay, so I will start with this, this Grover algorithm. So today I will present the algorithmic side of it, and maybe next class I will start more on the physics side of it. So Grover's algorithm is very much physics, okay, but you will not see that today clearly, okay, because I'll present the how it was presented first, but we have a good physics understanding of it, okay. Now. So what is the problem here? So the problem here is this reverse phone directory. Okay, so you have say, I mean, a lot of you are young people. Okay, so you have gone out, you have got heavily drunk. Okay, and you have taken someone's number and of course name and number. But next morning you can just call back and cannot remember the name, right? So you just say, hello. 7745 whatever, how are you, and that's not a good thing to do, right? So your task is to do this reverse phone directory search where you know the number, and from the number you have to find the name. Okay, now of course I don't know, these days of course you don't I mean my examples are always very dated ones, okay, because I started teaching these courses in 2004, 2005. So now, of course, you will look up Google, and maybe Google can do the reverse also pretty well, okay. So if you give the number, maybe it churns out a name, okay. But anyway, in general, unsorted. So the scientific, the right nomenclature is unsorted database. Okay, so the thing you want to search, you are given a number, you want to find out the person's name, but it's not sorted. Okay, it's also called needle in a haystack. Okay, that's what Grover called it. Okay, so what would the classical strategy be? Okay, so again, my example is a bit. So I mean, my illustrations are a bit dated. So you have, lots of phone numbers here. You will have some machine by which you are scanning one by one, and it says blip. Yeah, then you check up what is the number. Okay, so you have your number stored and you're going beep, then you find the name. Okay, and then it's very decent to call up that person. Okay, without any insult. Okay, so now so that is your black box here. Okay, so in Grover, the black box we assume is a rather powerful black box. Okay, and no one really knows how to make this quantum phone directory, okay, so that you can do that with the black box. But for the moment, we will assume such a black box exists. I will tell you maybe tomorrow the real applications of it. But so the black box, what it will do, if it finds a marked element, so the black box will, so let me write the problem then properly. Okay, given a black box which does, okay, so X goes to x if x not equal to m, and goes to minus of x if x equal to m. Okay, so m is the marked element. Okay, so x is like the phone number which you are with which you are marking the thing is stored somewhere. So the marked element is the one with which the phone number matches, the phone number stored by you. Okay, so it's not that you know any, you don't know the person's name, you just know the number, you know the thing with which it is marked. Okay, so once you find the marker, as you see, we can the function itself can say 1 or 0, yes or no. Okay, 1 or 0, but we know from this phase query black box we can put it in a phase also. Okay, so that is what is given. Okay, I'm not telling this black box is easy, okay, at this stage, but suppose this black box exists, okay, then the target is to find, okay. Now here is where people get confused, like you know the m or you want to find the m. It's not that you know the m. M has a marker which will give a blip. Okay, and then you will find what m is. Okay, so m inside it has a marker. So the thing is to find m. Okay, find m is like finding the name. Okay, the name is tagged along with the marker, which is the phone number. Okay, and when that phone number matches, the machine can give a minus sign. So the machine can say yes, this is. Okay, now classically you can see you can easily see that you will require at least of the order of this capital N uses of the black box. Okay, less than that you should not be able to do. Okay, because what will happen, you will you don't know at all where it is. Okay, so you will have to go through all those n. Okay, I think there are people collecting outside, right? Is there something here maybe? Okay, okay, yeah. Maybe I stop today. So we will start from the quantum. Okay. Okay. So yeah. So I think we will start from the quantum in the next class, the quantum algorithm, and then present some physics counterpart of that. Okay. Yeah, how you achieve this. So quantum algorithm will achieve it in order of square root of n essentially. Okay, but we will show how. Okay.
Thank you very much.
Okay.